Okay, so if you need to pause this, go ahead and pause it. So this is Lenz's law, where nature tries to resist current, or tries to resist any change in the magnetic flux. So as you're bringing the magnet through the ring, as you from the left side to the right side, nature is first going to make an arrow pointing to the right, because there's more magnetic flux coming through. As you push the magnet closer to the ring, so the red is the direction of Lenz's law, which is the nature inducing a magnetic field, which means we put our fingers in the direction that the red arrow is going, and we put our thumbs in the direction that the current is going to go, or the thumbs tell us the direction the current is going to go. So it's like we're grasping the ring, and then our fingers are pointing in the direction of the red arrow, so that it's going. The current is going to go in the same direction that it has already identified as the direction of positive current. So it's going to start out that way, which means it's going to start out positive, so we can cross off B and D right now. However, once the magnet gets to where it's directly in the middle, as you continue moving that magnet to the right, once it's gotten halfway through, you're now going to be decreasing the magnetic flux. Does that make sense? You're going to start decreasing the magnetic flux. So once you're on the other side of the magnet, nature is going to resist the decrease of the magnetic flux, and it's going to apply a new induced magnetic field in the same direction the magnet's moving. So now we'll use our right hand rule again, and we'll put our fingers in the direction of the magnetic field, and our thumbs are going to go in the direction of the current, which will actually be in the direction opposite the positive current. So it's going to start off getting positive, and then once it reaches that halfway point, it's going to start being negative again. Well, not again, because it wasn't ever negative to begin with. So that means that the answer is C. Okay, so again, if you need some time, go ahead and pause this. But the first thing that we need to ask ourselves is, in this situation, what is supplying this magnetic field? Is it going to be the current that's going through the wire? And you should see that if it's the current through the wire, then the magnetic field is going to be in opposite directions on either side of the wire, which is not the case here. So that means that something else is creating this magnetic field. So there's a magnet above the page and below the page. You can think about it like that. So that means we're going to use the right hand rule where our hands are open. So we're going to have our fingers going into the page, and then our thumbs are going to go in the direction that the current is going. So we have to decide, is the current moving to the left or is the current moving to the right? And for that, we should look for this battery. The current flows from positive to negative, so it's going from the positive side to the negative side, so it's going counterclockwise. So that means that when we're using our thumbs should be pointing to the left. Therefore, the magnetic force is going to be pointing down towards the bottom of the page. So the correct answer should be E. So what we want to do with this one is we should probably ask ourselves what's creating the magnetic field that they're talking about in this. Now, in the previous one, it had a magnetic field already drawn for us. So that was kind of a clue telling us that there was something else creating the magnetic, or there was something outside of this diagram creating the magnetic field. But in this diagram, there's nothing creating outside of the magnetic field. So the only thing that contributes to the magnetic field is the current going through the wire. So that means we're going to use our second right-hand rule, the one where we're grasping the wire. So we're going to take our thumbs and, well, let's talk about this one first. So we're going to take our thumbs and we're going to put them into the board, and then we want to line the tips of our fingers up with where the point P would be. And that's going to tell us the direction at that point P. So we don't want our thumbs, basically we don't want our fingers to tell us where the current is, or where the magnetic field is going to be over here, which would be in this direction. We want our fingers to tell us where the magnetic field is going to be here, which is going to be, it's going to be completely perpendicular to the direction that the magnetic field is going to be. Now we can do the same thing for this one, where we take our fingers and we go out of the page, and we take our thumb and we put it out of the page, and we take our fingers and align them with where point P is going to be, and the tips of our fingers tell us that the magnetic field is going to point in this direction for this one. So now if we're thinking about vectors, we can split these each into an x and a y component. So the x component for this arrow is going to completely cancel out the x component of this arrow. Does that make sense? And then we would be just left with the vertical components of both arrows. So the correct answer is A. Okay. So this one, once we've read it, we should really cross out anything with a meter stick in it, because that doesn't allow us to measure current or anything. I mean, if we could shrink down to the atomic level and use a stopwatch and a meter stick to measure how fast the electrons were going, then we could do something, but there's no way we can do that. So we should cross off anything with a meter stick. So that gets us to a 50-50. So you might say, well, I don't know what a meter stick or an ammeter are, because I haven't told you what they are yet. You might be able to figure out that a voltmeter measures volts.
No.
Yes. And an ammeter measures amps.
No way.
And you might say, well, if I want to measure current, amps is current, so I should choose the one with the ammeter. But something that you don't know is that to hook up an amp meter, you need to disconnect a circuit. So, like, if I draw a circuit diagram and I want to measure the current through it, I have to erase a section and put an amp meter in. So this is my little amp meter. So here's my little red in, and the out's coming. So an amp meter has to be connected in series into a circuit. A voltmeter does not. So if this question asked for how to measure the volts without, without disconnecting any wires, then I could use a voltmeter to measure the volts. But an ammeter needs to be connected in series to measure the current. So where it says disconnecting any wires, We should cross out that one. So the reason we can use a magnetic field sensor is if we measure the magnetic field here, we had a formula. Let's see, that formula was B equals, no, not the sine one, because that one's for the magnetic force, which is different than the magnetic field. It was, this is the one we're interested in. That's a 2 pi, sorry. 2 pi. We could use this formula. If we could measure the magnetic field with a magnetic sensor, then we just have to know how far away we are from the wire, and we can get our current. Okay, so something that I have not explained yet is electromotor force. That's what this EMF is. Basically, this is the force responsible for the electrons actually moving through a wire. And there's an equation that we can get that's the EMF, or the electromotive force, which is this symbol, is equal to the change in magnetic flux over the change in time. So for this particular problem, the change in magnetic flux is final, which is 0, minus initial, which is 0.3, so we end up getting a negative from here. We end up getting a negative 0.3 divided by the amount of time. So that's 0.3 divided by 2. And this is the electromotive force for 1 turn of a wire. So if we have 20 turns, then we need to multiply this by 20, and we will get the answer B.
And like